Right, so here we go. We're going to start learning how about polynomial functions. So we're going to have to graph this. So we're going to make a xy axis, and what we see here is I see that this function crosses the x-axis 3 times. I know it crosses it when x equals 0, because when x equals 0, so it's kind of like, let me step back. On those problem sets I've been having you solve quadratic equations, and in the book here, and you want to know, if this is the quadratic equation, where does that equal 0? Where does that cross the x-axis? So when x equals positive 2, when x equals negative 1, that's equal to 0. So those are the zeros, or the roots of this polynomial function. So what you could ask yourself is, where does this function cross the x-axis? So what values make that equal to 0, the y equal to 0? Well, I see one of them is 0. I see one of them is at positive 1, and another one is at negative 3. So we'll plot those points. Negative 3, 0, and 1. I exaggerated this a little bit. But then what you got to think about, well, let's see. If I expand that all out, I'm going to have an x to the 4th as a leading term. Right? So that I know the ending behavior looks like this, and then it's got some stuff going on in the middle that we don't quite know what's going on. We do now know that it crosses the x-axis at those points. So the question is how does it do that? Well, what you got to think about is, if I have just x squared, that comes down and that kisses the x-axis at x equals 0. And if I have x cubed, let me go to red ink, that wiggles through the x-axis like that. Flattens out, right? It flattens out and then heads back up in the same way. So whenever you see a factor that heads to the second power, that's going to behave just like the x squared graph. And Mr. Bruckner calls this that the graph comes down and bounces off the x-axis. So anytime it's a squared or to a 4th power, it bounces. If it's just to the 1st power, well, then it just passes through. The other thing you'll find in the book, when it talks about multiplicity, and what multiplicity is, now I want you to write that down in your notes here. Multiplicity is the power, and that's basically how many times it counts twice. I mean, because if you have x squared, x equals 0 is a multiplicity of 2, because there's 2 zeros, right? It's got to. We know that a quadratic equation has 2 answers. We know a 3rd degree equation has 3 answers. So in order to make it count, we got to talk about the multiplicity, is how many times that answer counts. So let's get back to graphing this. So I know the ending behavior of this function ends up like this. We just got to figure out what happens. So I know it goes through negative 3 once, because that multiplicity is 1. But then it goes through x equals 0 once. But it's supposed to be, somehow it's got to end up there and go through this point. Go through this point right here. So it's going to have to come back down, bounce off it, and head off to infinity. So it's going to come down, you bounce off it, and then head up to infinity. You try to make these nice smooth curves. Okay? So that's basically what it looks like. Yeah, we could get a little more exact, but this is the general idea, and that's good enough. With this function, I'm seeing this root has a multiplicity of 3 because it's to the 3rd power. So I know it crosses at x equals 2. I know it crosses at x equals 1, because that's negative 1, that's positive 2, right? It makes that zeros. If I expanded this all out, this would be an x to the 4th, right? So I know in the end, it's headed up just like this with the other one. But what's going to happen, and this is to the 1st power, so this is going to come down, pass through negative 1. But then, since the only other 0 is when x equals 2, we know it's going to come up, It's going to flatten out because that's what cubed, that's what, remember, y equals x cubed, but it's trying to imitate. That flattens out and then heads up. So we're trying to flatten this out and then head up to infinity. Now the only other thing that I could check on is, does this have, what's the y-intercept of this? Well, x equals 0 any place along that y-axis, right? So if I substitute in 0 here and 0 here, that's going to give me -8 times 1 is -8. So if I had had a better defined graph, I could pass that, make sure that passes through -8, 0, -8. Okay, so what's new about this is the multiplicity of 3. It's going to flatten out, finding the y-intercept, and of course the ending behavior we got to keep in mind. So now they're asking us to come up with some graphs. So what am I seeing here? So I'm seeing a double root here at -1. So that tells me it has a multiplicity 2. So the power will be 2. Here I'm just seeing a single root. So that has multiplicity 1. And then if I'm looking at this, I'm seeing something that looks like a cubic, an x to the third. And if you think about what you learned in section 1, I see 2 turning points. So that means the smallest power it could be was x equals 3, which works with what we've decided. So I know that it has a 0 at x equals -1. So let me think about that, write that out for you. If x equals -1, that gives me a factor of x plus 1, right? Equals 0. So x plus 1. But we know it has a multiplicity 2 because it bounces. At least we think it has a multiplicity 2. And then the x equals 3 is another 0, so x minus 3, right? And that has a multiplicity 1. Now the only other thing we got to worry about is some stretch factor. So there's probably an a in front of this. So what we need to do is figure out another point. Sometimes they're nice points. We could use this point. We could use this point. I'm going to choose to try. That looks like 1.5 to me, -1.5. Well, what's nice about that point is if x is 0, y is -3/2. -1.5. So that way I can just drop this in here, is -3/2 equals to a, and then here's where the beauty of it comes in. 0 plus 1 squared times 0 minus 3. If we had used this point, I would be sticking a 1 in for x, and y would be -4, which isn't impossible, but it makes it just a little bit harder. So this is going to give me what? -3/2 equals a times, let's see, 1 squared is 1, and times -3. So that is the same as -3/2 equals -3a. So I'm going to divide both sides by -3, which is the same as multiplying by -1/3. So that cancels out, that cancels out. I'm seeing 1/2. I think a is 1/2. So now, well, let me finish writing that. So 1/2 x plus 1 squared times x minus 3. And that's what f of x or y equals, I think. So earlier I graphed this. Okay, I don't know if you can see all that, but I'm seeing the 2 zeros. It bounces. It bounces. Let's see. It bounces, passes through. It grows through -1.5. So I think I did that correctly. Now for this one, I'm seeing a single root, so that has a multiplicity of 1 at x equals -3. So that's our factor x plus 3. Here it's not bouncing. Here it looks like it's flattening out. So I think that has a multiplicity of 3, the way it's acting like x cubed. So x plus 1, I'm going to raise that to the 3rd power. And then this one bounces, right? So it comes down to 2 and bounces, so that multiplicity 2. So x minus 2 squared. Now the thing I want to check at, I'm seeing an even-powered graph, right? The biggest exponent is going to be an even number. If I expand all this out, this would give me an x squared. This would give me an x cubed, and that's an x. So that's x to the 5th plus 1 is 6th. So that checks. Now the other thing I'm seeing, it has a y-intercept of 0, 1. So that'll let me find my a. So 1 equals a times 0 plus 3 is 3. 0 plus 1 cubed is still 1. And negative 2 squared, well, that's going to be 3. That's going to be 1. That's going to be 4. So 1 equals 12 times a, right? Because 4 times 3 is 12. And then I'm going to divide both sides by 12, so I think a is 1 over 12. So to put that back in perspective, let's see, I think, actually I'm going to be messy and write this as 1 over 12, just so I don't have to rewrite all that. Now if I try to, I did graph this earlier. See, that's the same. Let's see this bottom one. I guess you can't see that I had a squared here, but I did, right here. I did. And then if we look at the graph, does that graph match that one? I believe so. Goes through that y-intercept. So I was right, and that's the process. So this is asking us, when is this graph, this cubic equation, going to be under the x-axis, less than 0? So we can do this algebraically. Why not do it graphically? Negative 2 is a 0, positive 1 is a 0, and it's got multiplicity 2. This is a cubic function if I expand that all out. So this is going to look like this. Come down, bounce off the x-axis. So when is this graph below the x-axis? Actually, it's less than or equal to. So we can say from negative infinity until negative 2, and that's a closed bracket at negative 2 because it says equal to. And then we can say or, well, if this were just less than, we'd be done. But because it's equal to, we got to consider that point right there where it's equal to. So I would just put, I'm not quite sure the right way to do it. That's how I would write that answer. It's not really an interval, it's a point. Okay, so that's where it's negative. That's where this graph is less than 0. So this one, I can't take the square root of a negative number. I can take the square root of 0. So basically what this is asking me to do is, okay, you've got this polynomial. When is it bigger than or equal to 0? That's what it's asking me. So we can check the graph out. Let's see. It's got a double root at negative 3. It's got a single multiplicity 1 at 1, multiplicity 1 at 2. And this would be a 4th degree equation if I FOIL it all out. So that means it's going to be like this and like this in the end. So let's check this out. Now this has the double root right here. So I'm going to come down. I'm going to kiss that root. I'm going to bounce back away from it. I could also think about the y-intercept, right? If x equals 0, let's come down here. Isn't that going to be negative 2 times negative 1 is positive 2, and that 3 squared is 18, so it's going to cross through 0, 18. So if I had more graph paper, so I know it's going way up. Then it comes back down. Now this says that x equals positive 1, and it just says multiplicity 1. So we're going to pass through. Then we're going to turn around and head back up. So when is this graph greater than or equal to 0? Well, from negative infinity, there it's equal to 0, so that's okay. It's not dipping down below. And then it keeps going back up, and then it's equal to 0 again at 1. So we're going to go from negative infinity until 1, and we're going to make positive 1. And we're going to make that a hard bracket because of the equal to. and we're going to say or, and we get another hard bracket at 2, and we're headed to infinity. So that's the domain for this function. So you did a problem like this in Algebra 2, I'm pretty sure. You usually do. So what they're asking us to do is come up with an equation for the volume. We know that this cardboard is 14 inches long, and we're cutting squares out of it. And if we're cutting squares out of it, each of those squares are x long, or s long, or whatever variable you want out of it. But aren't I cutting out two? I'm cutting out two x's off that 14. So the length is 14 minus 2x. That's going to be this length right here. Because what we're doing is we're folding up this box, right, to look like this, cutting those corners out. And that's our box, right? Kind of lame. So this length right here is the same as that length right there, which is that 14 minus 2x. Then the width is that distance right there. Well, that whole thing is 11 long, but we're cutting out 2x. So that's 11 minus 2x. I'll rewrite that over here too. So 11 minus 2x. And then when we fold it up, isn't the height going to be just x? So our volume equation is going to be, so the volume based on x is going to be x, because that's the height, times the length, which is 14 minus 2x, times the width, which is 11 minus 2x. And we got to figure out what dimensions maximize this, right? So I know this graph crosses the x-axis at 7. I know it crosses at 5.5 and at 0. So I know it's a cubic. So it crosses here at 5.5 and at 7. So it's a cubic. All these are multiplicity 1. So it looks something like this. Now when x equals 7, that is impossible, right? So this whole distance is out, and that's negative. We aren't going to have a negative volume. So it must be the maximum value happens in this range, and most likely here. So at this point in our mathematical lives, really what you want to do is put this into a calculator, graph it, and look for that x value where there's a maximum. So I graphed that out in Desmos, and I knew that the maximum value was going to happen between 0 and 5.5, and that's what I'm seeing is right up there. Okay, so when x equals a little better than 2 inches, we know that'll maximize our volume. Okay?